neural control part 3, linear control in state space. Caveat, I know nothing about what I'm going to talk about. So in the last video I talked about the PID control, which stands for proportional, integral, and derivative control. So how they calculate the error. So error proportional, the correction term is like proportional to error or integrative or derivative of it. And then you can like control systems. But it doesn't really work well with like multi-input, multi-output for like, for example, something like this, where there are multiple inputs. Think of like a visual system where there's like so many different like 256 by 256 different pixels of visual input, and then there's some output of many different visual neurons giving some sort of output of different like firing rate and etc. So dynamical system reviews, general form of dynamical system, there's a x dot equal fxu, and this is like to represent like the states of the system, and this is the time derivative of the states, which kind of it includes the information about the time and then input up to the system. And this is where a first order differential equations, and output of the equation could be represented by y equals gx format, and this is like, it's pretty linear. And then this all we're trying to do is like, we're trying to make things like linear because it makes our life easier, and nonlinear stuff is really hard. So we have this x represented Rn, where it's the state as a state vector, and n and p are represented like dimensional. So n dimensional, m dimensional, p dimensional, but they are not necessarily all like same numbers. So if you have like 100, like 256 by 256 like visual pixel, and then we may have like just neurons, like 10 like visual neurons responding to it, and then they have like different dimensions. Anyway, and the f is just the Rn times Rm, becoming Rn, and then Rn, the state vector, turning into output vector. Okay, great. So dynamical system describes a lot. System evolved predictably in time, so we have like good models, and then the model is able to predict well. Knowledge of certain set of system variable completely characterize the motion of the system. So this is capturing everything. Every like variables called state variables. Think of, for like spring mass system, it could be like the time, the displacement, velocity, force, etc. So, and with all that, we are able to like model the spring mass system. And the effects of system inputs are not instantaneous. This effect also propagate predictably in time. Things propagate. So spring and damper, fly system, genetic expression, vehicle steering, predatory prey, and then neural activity. So the real things in like biology especially, it's not really linear. So but if we can approximate things to be linear, or if we just look at a very like limited range of time, things are so it's locally linear, so it's good enough. The stability of the linear system with no input. So if A is non-singular invertible full rank, the originality is only the equilibrium. So think of it like this like ball in this like curve, then this thing point is like the only equilibrium. So when x dot is 0, that means there's no change. So it's like the equilibrium. So that's why the BU goes into like 0, because nothing's changing. So that's just when x dot is equal to 0. And x is equal to 0, that's like the equilibrium. So we don't need this, because if this is x is 0, then x dot needs to be 0 as well. Eigenvalue of A determines the stability or origin. I don't really understand, but 2 by 2 matrix means it needs 2 eigenvalue. 3 by 3 matrix needs 3 eigenvalue. And if there's no like imaginary term, then if the imaginary terms are like smaller than 0, then it's like negative, then things are stable. But if it's like positive, then it's like unstable. But like eigenvalue gets complicated, so we look at the real part. Pendulum system, so we have the angular acceleration of theta dot dot, angular velocity of theta dot, and then theta of angular displacement. we have, so these are friction terms, gravity term, and that's equivalent to angular acceleration, and they are nonlinear system. So we put this in this matrices. X equal theta, angular displacement, angular velocity is x1 and x2, and we get this equation where x2 is x dot and x dot is this thing, and they're not linear. So we solve for x dot 1 and x dot 2 is 0, where nothing's are changing, which is an equilibrium point, and we solve for stuff. So we can think of it like x, like a sine equal to 0 or pi. You know, they're the 0. So this x dot 2 will so when they're both 0, 0, this x dot 2 is equal to 0, which is the angular acceleration, because we don't need an acceleration because this is an equilibrium and nothing's changing. So that makes sense. And so when this 0, 0, we get either the pendulum that's on the over here, or like the pi is equal 0. So sine pi is also 0, right? So and it's like upside down apparently. But so these are the pair of equilibrium points. Like the what do I call this thing? I forgot. But anyway, if you put it here, we can see like what's kind of happening, like how the system will occur and what point it will converge to, and yeah. So a pendulum example. So linearization and stability. So this is a nonlinear system. So like, how do we make it into a linear system? So this star is some sort of perturbation from external perturbation, and and we do Taylor series expansion and we get this somehow, and I don't really understand, but this thing is from previous equation. So x2 is just like this, x dot 2, and this is like x dot 1. So we are 0 and 1, and then that's where these terms like came from. So x1 and x2. So we get 0, 1, all this. So and this is x1 and x2, and when x cosine is equal to 0, it's just 1. So we get just the same thing over here. And the negative km, there's no x1 and x2 term, so it's over here, same thing. But when it's cosine is equal to pi, it's negative 1, so it's like negative sign goes away, and it's like unstable because eigenvalue is greater than 0 apparently. Yeah, and all these terms are like all positive values, so there's that. Linear dynamical system, so we talked about it. Trajectory analytical solution for linear time invariant cases is known. So this is like a solution from like I think the solution for this thing is like this, and like it's like known. And like this is important because like when the AT is like important, like e to the power of it, like AT, so let's say like T0 is like 0, and like if this is positive, like it's like increasing exponentially, right? And so like things like blow up and it's super unstable. So I think that's like kind of like the eigenvalue, and that's why we want eigenvalue to be like negative, so it like kind of degrade it into like some like stable points. And it's like, it's really important, a lot of advantage to making your system linear, because there are a lot of tools out there for linear system. Goal of feedback in state space stabilized on unstable equilibrium point. So there's a concept of controllability and reachability. Controllable is that if there's an input that can drive a system from like drive a system to like 0, and then the system is completely controllable if every state is controllable. And if states reachable means that if there's an input that can drive a system to like certain value you want, then and system is completely reachable if every state is reachable. And the controllability and reachability kind of like a trade-off. So state feedback to stabilizes the origin state feedback, or input is functional state for LDS, which stands for something. I think I'll get it pretty soon. So for this, we can keep the control state linear as a u equal minus kx. K is like x is the states, and use like the input going in here. K is like the stuff that kind of factor that make it into like useful input or feedback. So x dot equal ax plus bu. AB are properties of the system, but we can control k, and you can kind of like rearrange this since u is negative kx from over here. So ax minus b kx, and then we can make it so that a minus bk times x, and we can convert this into an a prime, and then so is it possible to choose k such that a minus bk has all negative real part eigenvalues, and they can be arbitrarily placed if the system is completely controllable. Controllable mean that we can drive the system to 0. We can do it easily in MATLAB. Just put like place a, b, and the poles, which is poles are eigenvalues. For controllability tests, we can do it so that b times ab times a squared times b times blah blah blah, and the a to the power n minus 1 times b is rank n. The system is controllable. Rank is kind of like an independency of the matrix. So if you have like say like 2 by 2 matrix, and then you make another like a row, so it's like 2 by 3 now, and then you make a third column into like maybe like the I don't know, like a just double of the second column or something. So it's kind of like independent. It's not independent. The third columns are not independent. They are like dependent to each other, and then the rank will be like lower. So something like that. Inverted pendulum example. So 4 states we have it. So positions and velocity of this cart, and then the angular velocity of this like pendulums. And this is nonlinear, but we can intuitively make the equilibrium points where the position of cart doesn't really matter, but what matters is the velocity of the cart to be 0. So when this system is stable, it's always unstable, but we need to reach equilibrium point, and at equilibrium point, cart is like not moving, and so is the pendulum, and then the angle would be like pi, so you'd be like upright 90 degrees. So position of cart not important, so leave it as x, be whatever it be, but velocity we want to be 0, so will be the angular velocity. But pendulums angles will be pi. And we can linearize around the pendulums, and there's a u term here, which is the force, and then s represent s equal 1 is pendulum up, minus 1 is pendulum down. This is like the friction on the like cart. And we can pick the eigenvalues or poles by trial and error, just like trying stuff, and there's this pole and this poles, etc. And then for this one, like the control is like too slow, and this is like happening pretty quick. Things to see is that the velocity, which is like the cart's velocity, should be going to 0, and then the angle, the omega, which is like the angle, and we want it to be like pi, or no, wait, what? No, the theta should be pi. Yeah, theta should be pi, which is the angle. So 3.14, yeah, reaching 3.14. And then omega should be like also 0, because it's like a velocity and we don't want things to be moving. And x should be kind of shooting for 1, desired location, so yeah, it's going to 1. So LQR, the linear quadratic regulator, is an optimal control strategy. So eigenvalue placement affects systems behavior under a controller. So we saw an example of this conservative versus aggressive control. So LQR is an optimal control scheme that places eigenvalue in a principled way. So like how aggressive, it's really asking like how aggressive do you want your control to be for it to be optimal. The cost function looks like the U is input, R is like the penalty and how aggressive the control is. So it is inversely proportional to the aggressiveness of control, right? So if the R is really big, so the penalty for aggressive control is big, so it'd be more like slow control. Whereas if R is really small and there's no cost in controlling it aggressively, then it should be like more like that. And so in certain application where things are really delicate and we don't want it to be too aggressively control, we would need like something like that, slow control. Now QX is like the steady state error or tolerance for error. So constant distance between the actual state and the desired state is what this is, and this is a cost of the controller effort weighted by our matrix. And LQR continued, the controller which minimizes our cost function is known, and there are algorithms to find it. So this is the optimal controller, which is linear, which is great. This K is the optimal K, and that's how we find this like K for this optimal controller. And the optimal K could be found with this equation. R, we know what that is, and B and S are like, S is like up and down, and B is like from the system itself. And we know R is like just the cost, what was this? The penalty on how aggressive the control is. And so there we go. And then like how do we get like what S is? And S is like you get this by this equation. And so U is, so Q and R is like chosen by like the system you have, which is like this Q and R, and then A is like from the system, and as you solve for it, so you get the S, and then you put it in here, and you get the K, and you put this K over back in here to get the like the optimal controller. In the MATLAB, they do all this math for you by just typing K equal LQR, and then AVQR. You put it in there. Great. Inverted pendulum example. So controller effort is really small, really big. We saw it a small cost and controller effort, so there's no penalty in like controlling aggressively. So like reach steady state it's just by 5-second mark, whereas the controller effort is huge, and then it may be steady state by maybe like 13 seconds. Great. So in real life, we don't really know the like state of the stuff. We can kind of estimate it. Great. So state feedback without observing the state. State estimation. So in general, y is not directly equal to x. There's no direct access to x, the state. So we have to kind of infer to it. So given the output y, we have to kind of estimate the state x, knowing the system's dynamics. Observability, so it's like, so unobservable, state is unobservable if the y, so the output is identical to 0 with x is equal to like x0. Because the state trajectory from initial condition leaves no signal in the output. So like you did like something worked like really well, and like, or like if the output is like 0, like nothing, then like how are you gonna know? Because there's like no trace. Like how are you gonna know the state? So a system is completely observable if the only unobservable state is like x0 equal. But if the state, if like things are perfect, like, and then we get like no output for it, then we know like things are perfect. But when there's a tiny imperfection and we get some sort of output beside it, then like we know it's like something's wrong. And in that case, it's completely observable. It is completely observable, and there's the test for like linear system, rank n, and then the system is observable, full state estimation. This is so freaking long. Full state estimation. There's prediction and the measurement, where kf is the gain, and this is a measurement, y is the measurement output, and this is predicted like output, and then you get the differences, and then you get to like multiply by this k factor, and then you get the measurement. And then there's some predictions, and then the x dot is the state. That's how you get like this. You're going through the full state estimator, and you like solve it for like this thing, and the y is replaced with this thing, CX, and then like you get this linear dynamical system where UI is the input. And then let error be the x minus x, this thingy, arrow, and then you solve it, and then so what you're saying is that if the system is observable, we can choose kf, the factor that this is like error like derivative, right? So if you know things well, you can choose this so that like this negative, the kf times c is equal to a, and this will eventually go to 0. Oh, great. Or so there's some Gaussian noise, but in real life we have a bunch of noises, so we have to add like Gaussian noise term, which is like this stuff. So this means like average of the white noise is 0, and then there's some standard deviation. Cost function to minimize variance in the state prediction error. Once again, you can use get the kf term, the common gain, through this MATLAB function. Pretty easy, apparently. And then this is like from, so what's happening? So we have this u and y coming in. That's the input going here, and then this common estimator. So there's the kf, and then like this stuff x up, and I guess the kf times c minus like a at that. So a minus the kfc. And it goes into here, and then we get some sort of output here, and that's what it's representing in the like actual term. Plant is the real system, by the way. But yeah. How does this dynamic system relate to the neuroscience? Well, we'll talk about it in the next lecture.